Hi, my name is Jazmine, and my team members are Amal, Alex, Kevin, and Meagan. Our advisor is Dr. Wang, and our project is a recycled 3D printing filament extrusion system. The growth of the 3D printing industry has had an impact on the environment. PLA, the standard printer material, is marketed as biodegradable and recyclable, but this is misleading since they are exempt from most municipal recycling programs. An approximate 6 to 19% of 3D printing projects end up as waste, amounting to 8 million kilograms of waste in 2020. PLA composting and recycling is a lengthy process and they create issues in recycling centers. Since PLA is classified as a Type 7 plastic, there are only around 100 industrial facilities in the U.S. capable of recycling it, but they do not accept residential waste. To minimize waste impacts and costs, more accessible methods of recycling filament are needed. With our recycled 3D printing filament extrusion system, we aim to raise concern about the environmental impacts of fused filament fabrication and fused deposition modeling printing, despite them being branded as environmentally friendly. By recycling waste filament, we will reduce waste from failed, unwanted, and testing prints, as well as help reduce waste costs. Our project will enable individual users to design their own filaments at home, and we hope to inspire the public to be more environmentally conscious by using filament extrusion systems.
The main system of our project is the single screw extruder. They are commonly used in the plastic injection molding and extrusion industry. The barrel heat profile is divided into three distinct regions. The feed region, where the plastic enters the barrel, the transition region, where the plastic transitions from a solid to a viscous polymer, and the metering region, where the plastic is fully melted and mixed. The system features PID temperature control and water cooling.
There have been an enormous amount of constraints and requirements our team has worked hard to meet. The type of materials utilized in this project do not typically come cheap, and to stay within budget has been a challenge from day one. Additionally, it has been absolutely crucial that we were able to meet the high temperature requirement in order to melt the PLA plastic. Motors, on the other hand, were not the biggest barrier to entry, but have maintained a level of complexity, such as proper output torque and winding speed. Above all, a consistent dimensional accuracy for the extruded filament has been top priority, since those measurements have no room to budge.
Fluid dynamics and flow simulation of the injection molding process is quite complex considering the flow is transient with a moving boundary and the fluid is non-Newtonian. For simplicity, the focus is on the behavior at the nozzle. CFD was used to predict an estimated flow rate to be produced by the motor in order to maintain a consistent filament. In regard to heat transfer, MATLAB simulations concluded that 3 heater bands are sufficient to transition the PLA in this system. 2 bands are located on the steel barrel, while 1 is on the brass nozzle, to create an ascending heat profile typically used in injection molding. Through convection and conduction, the polymer is heated to a viscous state upon reaching the nozzle exit.
Here's an overall schematic of the circuitry for our project. This layout makes strong use of solid-state relays in conjunction with the Arduino, allowing the microcontroller to turn on and off the heater bands that require high wattage to reach 180 degrees Celsius. Additionally, the microcontroller makes use of 2 K-type thermocouples, an RPM sensor, a stepper motor for our winder, and lastly, a Bluetooth module. The other half of the circuit diagram consists of an AC motor and a relay box. Since this motor has no smart functionality, we decided to adjust the motor speed by having the Arduino measure the RPMs, and turn the power on or off to the motor circuit via the relay box. This box also provides an extra layer of protection from drawing too much current from the wall. The Arduino adds a whole new layer of intelligence and security to the system. Utilizing the diverse libraries from its ecosystem, we are able to have complete control over the entire project pipeline. Each sensor provides feedback that we can then use to tweak how the plastic behaves from end to end. A great example of this is the PID temperature control. In conjunction with the K-type thermocouples, the Arduino can intelligently and gently bring the heater bands to a desired temperature and maintain equilibrium. Additionally, using a Bluetooth module, we are able to output all data over the air. The Graphical User Interface, or GUI, for our project is a custom iPhone application. Here the user is able to have a quick glance at all the sensors connected to the Arduino in order to ensure all systems are running as expected. It is important to have this level of functionality because a user should not be expected to stand in front of the machine the entire time during its operation. So why Bluetooth functionality? Bluetooth Low Energy, or BLE, is an extremely common and robust technology that utilizes low power, allows for reasonable distance of data exchange, and supports mesh networks allowing up to tens of thousands of devices. Working within Bluetooth, there is a hierarchical structure containing services and characteristics. Those characteristics can be exchanged between the central manager, our iPhone application, and the peripheral, our Bluetooth module, giving an easy-to-use pipeline of information sharing between our extruder and graphical user interface.
The most distinctive feature in the first iteration is how it operated vertically. At first, the team believed having gravity act in the direction of flow would be beneficial. However, research showed that most extrusion systems operate horizontally. Doing this allows for easier post-processing of the filament. As discussed, the second iteration changed to operating horizontally. After finite element analysis, it was decided to add an additional heater band to the steel barrel. This iteration included a smaller hopper than the one used in the final design.
The final design of our project uses a high torque AC motor water cooling line, and an ascending heat profile. The 3D printed components are made from PETG to ensure that they will not melt. The system uses a rail-based mounting system to keep all of the components aligned. The metering region at the nozzle and the extruder barrel have individual temperature control.
There were a few challenges that we as a group have faced throughout these 2 semesters. Some are by not having access to a CNC milling machine, welder, or lathe. Having an Arduino-based PID temperature control led to overheating due to timing delays. Funding and timing constraints are the other 2 main challenges we incurred in difficult times by not being able to meet up in person and having longer lead time on ordered parts. Future work and improvement for this project includes the completion of the filament diameter measurement system pulling and spooling mechanism. Some other improvements include upgrading the wood boring screw to an extrusion screw, switching to a standalone PID controller, using heat blocks for proper thermocouple mounting insulation for the extruder barrel, and metal thrust bearings. One important future work would be to incorporate other type of plastics for recycling using our system.
Thank you for listening to our presentation. We also owe great thanks to our advisor, Dr. Wang, for kindly guiding us through this project.